And so before we introduce the AD9375, which is ADI's solution to this problem, I'd like to take a step back and look at what we released in June of 2016. So the predecessor to the AD9375 is the AD9371, introduced in June 2016, replacing 20 discrete parts. So this is a wideband RF transceiver, high performance. It implements 2 receivers, 2 transmitters, an OBS path, LO generation and clock generation, all on a single chip. And what the diagram is showing here on the left is a discrete signal chain architecture that many would have built up in the past when trying to implement this functionality. And it's pretty large. It's about the size of an A4 piece of paper. And what we've managed to reduce that down to is a 12 by 12 millimeter BGA in the case of the AD9371. So all of that functionality is implemented at a fraction of the size and power consumption of the previous discrete solutions. So that in itself was a breakthrough in terms of the technology. So, and this year we're going one step further to introduce the AD9375, and this is the world's first wideband RF transceiver with integrated DPD, or digital predistortion. So what this does is it takes the device we introduced last year, the AD9371, and integrates a DPD algorithm on chip while remaining pin compatible with the AD9371 and not increasing the power consumption, which is quite an achievement. So looking through some of the details, the DPD signal bandwidth is 40 megahertz. It supports 3G and 4G waveforms, both TDD and FDD operation, and a tuning range of 300 megahertz to 6 gigahertz. So all in all, this represents a great common platform device that can be used across a range of different modes, 3G and 4G, TDD and FDD, and then across all of the sub-6 gigahertz 3GPP bands. The receivers have a total bandwidth of 100 megahertz with a noise figure of 12.5 dB and an input IP3 of 22 dBm. So these are designed to be used with an external low noise amplifier. The transmitters have a total synthesis bandwidth of 250 megahertz to allow for digital predistortion energy, an output power of plus 7 dBm, and an OIP3 of plus 27 dBm. So the raw linearity of the device is excellent. The observation path is then used to observe the output of the power amplifier that has a bandwidth matching the transmit synthesis bandwidth, and that has 2 inputs. Just like the AD9371, the transmit, receive, and observation path LOs are fully integrated. We have transmit and receive quadrature error correction, DC offset, LO leakage, all implemented on chip. And programming is via an API which abstracts a lot of the underlying complexity of the device and gives some simple interface to the device. We have included a transmit closed-loop gain control and VSWR VSWR monitor on chip. So the closed-loop gain control maintains the transmit output power at a pre-programmed level, accounting for temperature drift, voltage drift, etc. And then the VSWR monitor can be used to monitor the antenna health, and typically that's used simply to monitor whether or not the antenna has actually been connected. Because if the antenna hasn't been connected to the small cell, you don't want to output any power because it'll just blow the PA. The interface is a 6 gigabit per second industry standard JSD204B interface. So that interfaces to many FPGA-based solutions. And the power consumption is 4.8 watts at the maximum bandwidth. And as we've been talking about, the target applications here are small cell base stations and massive MIMO or active antenna systems. So what are the benefits of integrating the DPD with the AD9375? Well, this is an ultra-low power DPD implementation that we put together. It reduces the DPD power by 90% over FPGA-based solutions. It cuts the number of SERDES or interface lanes in half, and I'll talk a little more about that in a minute. All of this means that the FPGA in the system requires fewer FPGA resources, which reduces FPGA complexity and system cost. So that's the device benefits. Then we wrap around it some elements to provide ease of use. So we have a tested PA library, which I'll talk about. I talked a little bit about the API, which abstracts a lot of the underlying complexity of the device. And then we have the usual evaluation kits, and of course, customer support is available. And in order to further accelerate time to market, we have also provided a small cell radio reference design that implements the 89375 alongside everything else that's required for a small cell radio. And I'll talk a little bit more about that as well. So what integrating the DPD really does is it enables a smarter system partition. So what we're looking at here is a 2-transmit, 2-receive implementation. So on the left-hand side, you have a traditional system partition where DPD resides in an FPGA. The FPGA generates the pre-distorted signal and passes it over to the transceiver via the high-speed SERDES lanes. And that goes out to the PA. The PA output is then observed, and the data is sent back via the transceiver to the FPGA for processing and for the DPD algorithm engine, and that closes the loop then on chip on the FPGA. So by integrating the DPD in the transceiver then, if you look to the right, we close that loop on chip. So the FPGA no longer needs to send over wide bandwidth data to the transceiver with pre-distorted data. All of the bandwidth expansion occurs on chip in the AD9375. And also the observation path data no longer needs to go over to the FPGA. So we close that loop completely on chip. So this is a smarter system partition. It reduces the number of SERDES lanes from 8 down to 4, and that represents power savings of 600 milliwatts on the interface alone. So these power and SERDES lane savings then scale as you move to 64 transmit, 64 receive massive MIMO base station systems. So on the left, what we're showing is, I guess, 32 instantiations of the of what was showing in the previous slide, and all of that sums up to 384 SERDES lanes that would have to be implemented in that 64 transmit, 64 receive massive MIMO system. If you move to the right then, where we close the loop on chip and reduce the number of SERDES lanes, you go down to 128 SERDES lanes, and that represents a total of 19 watts in power savings. It's important to note, just for simplicity, we've only shown that the lanes here necessary for transmit and observation in this particular diagram. Okay, so what kind of typical performance can be achieved with this digital pre-distortion solution? So what we're showing here is an LDMOS DOR TPA with 42% drain efficiency, operating at 2.4 gigahertz in the 2.4 gigahertz band. The output power is 38 dBm average, or RMS, and the peak to average ratio of the signal is 7.5 dB. So on the left, you've got the pre-DPD ACLR, which is about minus 28 dBc. And for reference, the 3GPP emissions in the adjacent band are, the allowed emissions are minus 45 dBc. So it's about 17 dB away from the specification. And then on the right, as you enable the DPD, the pre-distortion solution kicks in and you get a 24 dB improvement in the ACLR down to minus 52 dBc, leaving a good margin to the minus 45 dBc specification. So what happens then as we increase the bandwidth to 40 megahertz? So what we're looking at here is an LDMOS DOR TPA again, operating at about the same drain efficiency, this time in the 2.6 gigahertz band and about the same output power. We're implementing two 20 megahertz LTE carriers adjacent, as you can see in the left-hand side diagram. So they're adjacent to each other. And the ACLR before DPD is minus 28 dBc. And then after we turn on the DPD, as you move to the right, the ACLR has improved to minus 50 dBc. So a 22 dB improvement in the ACLR.